Hi, my name is Netoff, and I'm an assistant professor of biomedical engineering at the University of Minnesota. Today I'm presenting a short video of my paper that was recently published titled Seizure Prediction with Spectral Power of EEG Using Cost-Sensitive Support Vector Machines, published with Parhi, Lan Lau, and Yun Park. This research was inspired by Varela's group in the 1990s, where they discovered that they could distinguish interictal EEG from EEG taken just prior to a seizure using nonlinear measures. In this paper with Kristen Jerger in 2001, we decided to test whether linear features such as power spectrum of the EEG could also detect changes prior to a seizure just as well as the linear. And we found that, in fact, when we compared the nonlinear measures with surrogates, where we scrambled the phases of the signal, that we got just the same prediction as with the raw nonlinear measures, indicating to us that the linear measures were probably sufficient for detecting the changes in the EEG. In this excellent review by Mormon, he went through the current literature up to 2007 and found that there was little evidence that nonlinear features could outperform linear features. And in fact, gamma band frequency power seemed to be the best predictor of seizure onset. A few years ago, Parhi from the Electrical and Computer Engineering Department at University of Minnesota approached me and asked me if I was interested in doing any data classification of biological signals. And I told him that there's this outstanding problem of seizure prediction, trying to distinguish preictal EEG from interictal EEG, and I thought that machine learning applied to linear measures of EEG might be a good way to approach this problem. We decided to make use of the Freiburg database, which was generated from the first International Seizure Prediction Conference, so that people can test their algorithms on the exact same database. And it labels all the electrode positions and the seizure onsets and any artifacts, and is a very nice data set expressly for this purpose. So the first thing we had to decide was how to prepare the data. And we could just take the raw EEG and take the power spectrum of it and divide it into different frequency bands and record the amount of power at the different frequency bands. So that's what you see in column A. In column B, we decided that we probably should take the difference between two neighboring electrodes to remove signals that have been measured on the reference electrode. And so that's what you see in column B. One of the problems when you're looking up at the power spectrum is you can see there's a fairly quick fall off in the power as a function of the frequency. So one way to make the power at all frequencies more similar is to take a time difference of the EEG, and the power spectrum on those are much flatter, and that's what you see in column C. And in column D, we did both a bipolar difference as well as time difference. To distinguish between the interictal EEG and the preictal EEG, we decided to use support vector machine, which is a type of machine learning algorithm that was developed by Vapnik in 1995. And essentially, we take all of the points, label them as either interictal or class 1 and preictal as class 2, and give the data to the algorithm, and it tries to find a vector through space which separates the two data sets. Each point here represents a different window of data, where one dimension represents the power in that window in one frequency band and another axis is in another frequency band. We recorded 20-second windows and the power spectra for 9 different frequency bands, which results in, across all 6 electrodes, 54 different frequency bands. And in such a high-dimensional system, you need a computer algorithm to find the dividing line. This flowchart represents the whole design of the project. So for each patient, we take the data, we remove noise, and then we calculate the power spectra across each electrode, and that creates the 54 features. And then we divide the data set into 3 different groups. One group is the learning set, where we actually train the support vector machine. And then we use another set of data to test that algorithm. And there's a couple parameters of the support vector machine, which I'll talk about later, which we can optimize over. And once the algorithm is optimized, then we test the algorithm on a final data set. The support vector machine produces a result trying to classify it. We find that that's kind of noisy, so we do some post-processing and then make our final seizure prediction from the process data. The use of this training data set, the valid data set, and the learning data set was suggested by our colleague Vladimir Tchaikovsky, who wrote a great book, Learning from Data. And it's called a double cross-validation scheme. And we don't really see many people using this, and it really makes sense. The algorithm really tries to separate the training and the optimization of the algorithm from the actual testing of the data. So we want to leave the test data completely untouched until the very end. And it's very easy to actually use the test data set in the optimization, but that will increase your seizure prediction results over what you would expect to see in the real-world situations. One of the keys to the success of our algorithm was tuning the support vector machine for the particular data set. We tested the algorithm over a range of costs for false positives, and we also tested over a range of ratio of misclassification of the data sets, i.e. identifying a preictal as interictal or interictal as a preictal. It's probably worse to miss a seizure than it is to have false positives. So we want to adjust the weight of the false positive rates to the false negative rates to make them acceptable. We use an F-beta test to measure the success of the algorithm, and it's a weighted version of the true positives and the false positives. And we set this at a value where we thought we had an acceptable number of false positives for every true positive that the seizure detector detects. As you can see, as we vary the cost and the ratio, we get varying levels of performance. So for each patient, we tested these costs and ratios and optimized for the maximum F-beta, where we set beta at the rate that we found acceptable false positive performance. The support vector machine outputs a value which is the distance of each point from the plane in space that's separating the two classes of data. And if the point is on one side, you get a positive value, and if it's on the other side, it's a negative value. So it actually gives you a continuous measure of which usually you threshold at 0 to decide whether you are in one class or the other. And we found that that measure, because EEG is noisy and your estimate of the spectra are noisy, that it varied quite a bit from time point to time point. So you can see here in panel A the output of the support vector machine's actual values in cyan. And you can see it's a noisy measure. The purple line shows you what we consider the actual preictal period, and there's several crossings of the 0 line before that. In B, you can see the support vector machine predictions just in an interictal period. But by taking a Kalman filter, we can actually smooth the data out quite a bit and eliminate a lot of those short crossings of the 0 line. And this really reduced our false positive rate significantly. Here's a table of our results where you can see for each patient the number of seizures, total of 30 seizures, amount of interictal hours, which 433. And you can see the success rates of detections, false positive rates, and p-values for each one of those false positives or true positives for the raw, bipolar, time difference, and bipolar differential. And it looks like their highest sensitivity was around 97.5%, and with the false positive rates around 13%, or one false positive every 6 or 8 hours. So this prediction rate is pretty high. There's a few patients for which we don't detect all the seizures, and the p-values indicate that we're not really doing better than chance. We're just detecting a lot. But there's actually quite a few, about 16 patients, for which we really think we are detecting a preictal state. Now you might realize that we're not actually making a real hard prediction Prediction is usually defined as identifying a window in time in which a seizure will occur. In fact, this is really anticipation rather than prediction, because all we're doing is identifying a change in the EEG leading up to a seizure and not predicting exactly when the seizure will occur. So finally, I'd like to thank the Institute of Engineering and Medicine, which gave us a grant to support Yun Park, who's the first author on this paper and a grad student in the ECE department who did a tremendous amount of work on this. The Minnesota Supercomputer Institute, who allowed us to use their clusters of computer to do a tremendous amount of number crunching. We've had lots of technical discussions with Medtronic about this work, and they've had some advice to give us, though they've never actually given us support on it. And then collaborators Vladimir Tchaikovsky, Tom Henry, and Greg Worrell, who we've talked to about this project all the way through it and have had very useful discussions with them. Of course, you can go to the paper to read more details, or please send me an email at tnetoff@umn.edu if you have any questions.